So the meeting is being recorded. So my name is Allison Towner. I'm a postdoc here at the University of Arizona, one of the organizers of the Origin Seminar. It is my pleasure to introduce to you today Desmond Jeff. Desmond is an NRAO Grote Reaper Doctoral Fellow at NRAO Charlottesville and also a PhD candidate at the University of Florida. He received his bachelor's degree in physics from the University of Houston in 2018 and his master's degree in astronomy from the University of Florida in 2022. Broadly, he is interested in star formation in extreme environments with an emphasis on massive star formation in the central molecular zones of massive galaxies, including in the Milky Way, the CMZ in the Milky Way. He's a member of the ALMA CMZ Exploration Survey, or ACES, that collaboration, and also the ALMA IMF Large Program. As a Reaper Fellow, Desmond is working with Dr. Jeff Mangum to leverage resolved observations of protostellar cores in the Milky Way CMZ to constrain the degree to which massive protostellar feedback contributes to the chemistry and physics of the CMZ of the starburst galaxy NGC 253. At the University of Florida, Desmond's advisor is Dr. Adam Ginsberg, with whom he is working in the ACES and ALMA IMF collaborations. So today, Desmond will be talking to us about thermal properties of the hot core population in Sagittarius B2 deep south. Don't worry, it gets finer grained. This is also the subject of a recent paper, which you can find on arXiv and ADS. So Desmond, take it away.
Okay. Well, thank you for that introduction, Allison, and just want to say thank you for the invitation and for all the organizers for inviting me to come and speak today. I apologize if I'm maybe speaking a little bit lower than I would like to. Just finding a quiet place where I can do this today has been a lot more complicated than I was expecting for it to be. But yeah, like Allison mentioned, today I'm going to be talking to you a bit about my work studying the thermal properties of the hot core population in Sagittarius B2 deep south. So just kind of jumping right into it, if I can move. There we go. In terms of sort of the motivation of this work, massive stars are vitally important to the physical and chemical evolution of their host galaxies by the formation of heavy elements in their cores over the course of their lifetimes, the dispersal of those elements upon those stars' deaths in their supernovae, and also the injection of mechanical feedback from the supernova, and also the ionizing and thermal feedback that they release over the course of their lifetimes. But in spite of their importance, we don't have the best formation process, or we don't have the best understanding of the formation processes of massive stars, and that's mired in part by several observational challenges, namely, just as an example here from canonical initial mass function, massive stars are rarer than their lower mass counterparts, and so correspondingly, the sites that form them also are typically further away. And also the earliest phases of massive star formation are also heavily embedded. And so all of those things kind of confound our ability to create a detailed model of massive star formation. But we try and do the best we can. And so it behooves us to look at regions of active massive star formation that we can see to place some constraints and gain some insights into some of the questions of how you make a massive star. One of the objects and phases of massive star formation of interest is the hot molecular core phase, or the hot core phase. These are objects that are massive and warm and notably chemically enriched objects that are thought of as the precursors to H2 regions. And so you can think about them as like the progenitors of high mass stars. And so just I have here a picture from the Mott et al. Review showing a canonical high mass protostar, but also a canonical hot core. You have your protostar in the center, it's accreting material from the surrounding envelope, and it's driving an outflow or something like that, right? What's particularly notable about hot cores is that they show a very high density, line density of complex organic molecules, or COMs. These are molecules that have typically 6 atoms or more, and hot cores show extremely rich spectra. So just to have an example spectra that I pulled from one of the hot cores that I'll be talking about later today, where you can see there's just a ton of lines. Managed to identify several of the species that are present in this hot core, but you can see some of the lines are still unidentified. Trying to disentangle all of them and give them names was difficult in its own right. The origins of this line richness is attributed to thermal feedback from the central powering protostar. And so just the basic idea is that there are ices that are present on the surfaces of dust grains. There's a ton of chemistry that happens on the surface of the ice, inside the ice mantle, and you can have the formation of increasingly complex molecules inside the icy mantle. As the protostar grows, it begins to heat up its surroundings, and you get to a point to where the ice on the grain will sublimate off of the grain surface and out into the gas phase. And then once you reach a particular density and temperature threshold, you start seeing them in emission. And so you just, as the protostar evolves, you reach this kind of critical phase to where you just have this flourishing spectra where the ices are all being sublimated off, and you just see what was being made on the grain surfaces. But the exact kind of cadence for how that process takes place in outside of the more like that canonical picture in terms of like, which molecules sublimate first, what processes are they tracing, how long do they live in the gas phase before they get destroyed, what destroys them, all of those things are still relatively not understood. And so that opens the door for us, of course, to be able to try and provide some insight by studying the hot cores directly. A great place to look if you want to study the early phases of massive star formation is the massive molecular cloud. Sorry if you hear any noises, by the way. But is the massive molecular cloud, Sagittarius B2 or Sag B2, is the most massive molecular cloud in the galaxy and the most actively star-forming cloud in the galaxy. It's located in our galaxy's central molecular zone, or CMZ, about 100 parsecs away from the galactic, or from Sag star. What makes this cloud particularly interesting is that the conditions that are present in the cloud are comparable to the ones that were present during the era of the peak of cosmic star formation, cosmic noon, around redshift of 2 or so. And so the advantages of studying Sag B2 is that we can study how the star formation process proceeded in a resolved fashion during this era, in conditions that are comparable to the ones when the majority of stars were formed. And just to have a picture here from Ginsburg et al. 2018 that shows the 3 mm emission from Sag B2, and just all of the different subregions are labeled. The different regions are labeled based on the relative position to each other on the sky. So we have Sag B2 north, or N in the north, M or main in the middle, S or south in the south, and then deep south in the deep south. Of particularly interest to us is the deep south region of Sag B2, within which were discovered more than 200 YSOs, or young stellar objects, and several of which were identified as hot candidates in the 2018 study. And just here's a zoom-in picture of Sag B2 deep south with all of the identified YSOs throughout the area. And so what we set out to do basically was to catalog the hot cores that could be present in Sag B2 Deep South, measure their physical characteristics, and then from those physical characteristics, try to compare to the hot cores that are present in the galactic disk to investigate the influence of the CMZ's extreme environment on the massive star formation process. And so the way we actually go about doing that in more detail is by using methanol as our thermometer molecule. We choose methanol because it is one of the simplest, if not the simplest, complex organic molecule. It is the parent molecule of several higher complexity molecules like dimethyl ether, methylformate, if you've heard of those, and many others. And namely, because of its simplicity and its relative abundance in the ISM, it's used in COM studies as the baseline when investigating the abundances of other COMs, because there are challenges, of course, in measuring the density of molecular hydrogen in places for various reasons. You can benchmark your COM densities against methanol instead to kind of get around the problem. So the way we do that is pretty straightforward, and some of you are probably familiar with this, but just we measure the intensities of each of the methanol emission lines that are present in our data set, and we use that to compute the column density of gas that's in the upper energy level of that transition. Assuming LTE, if you plot those column densities on a plot with or as a function of the energy level of each transition, and you fit a line to the distribution that you get. The slope of the line gives you the temperature parcel of gas you're looking at, and the intercept gives you the total column density of the parcel of gas in that area. And here I just have an example of one of those diagrams called rotational diagram, where the blue points are the upper state column density measurements we make. The orange is the LTE linear fit, and the black lines, excuse me, are a bunch of bootstrap samples of the distribution to try to better gauge the range of possible temperatures and column densities that we measure based on this distribution. And so those factor into the error measurement that we get. And so doing that, you have a temperature and a column density. If you do that on a pixel-wise basis, you can generate a nice resolved temperature map for your hot cores, and we will be able to use that for the rest of the analysis. As one additional sanity check, we also validate the line optical depths for all the lines that we're looking at after making this measurement. And so just here is this plot where you see the optical depth on the y-axis, and then the column density divided by the degeneracy, log of the column density divided by the degeneracy, the x-axis for a range of temperatures. And so using this plot, we're able to say that all the lines that we're looking at with the methanol for the temperatures that we're measuring are all optically thin. And so we don't have to worry about concerns about, underestimating what the temperature might be because the lines may be optically thick or something. We would have to be overestimating the temperature by many, many factors greater than the constraints that those temperatures give us imply in terms of being able to simulate other lines, for example, or simulate other molecules using these temperatures. And so we're able to be pretty confident that the temperatures we measure are a reasonable measurement of the temperatures in the hot cores. And so just moving into the results directly, this is kind of a summary plot of all of the measurements that I have done across Sgr B2 Deep South. So just to explain, the middle plot is the 1 millimeter dust continuum through ALMA that we measure across all of Sgr B2 Deep South. The inner insets are zoom-ins on each of the hot cores that we studied in this work. And the red contours on those represent any areas where the brightness temperature of the dust was higher than 12 Kelvin. In the outer outsets are the actual temperature measurements that we measure, or sorry, the actual temperature measurements from methanol with the same contours overlaid on them as well. So in detail, we discovered 9 new molecular cores throughout Sgr B2 Deep South, and we also did the methanol temperature measurement and such on the Sgr B2S as well, since it is also in this region. They show just a range of properties, like the temperatures are between 250 and 430 Kelvin or so. Sgr B2S is more of a hot core cluster of sorts. We didn't have the resolution and line data to actually disentangle like the individual components of the source, but the peak temperature in that source is around 660 Kelvin. The radii range between 360 and 670 or 6700 AU, with Sgr B2S having around 10,000 AU radius. And the masses are between 200 and 2,000 solar masses, with Sgr B2S around 4,800 solar masses. And just on the right here, I have two of the temperature maps that helped kind of form the backbone of all of this for the hot cores, DS1 on the top and DS7 on the bottom. And as you can see, you have a nice kind of central hotspot and surrounded by these, hot gas surrounding the rest of the core. To quantify this a little bit more deeply, we generate radial density profiles for each of our sources, and we fit radial power law indices to them, notably in the comparison set that we looked at for this work, which I'll get to a little bit later, but they fit single power laws to their radial temperature profiles. We find that we are better able to reproduce the distribution with broken power laws instead, where the power law break occurs somewhere between 2000 and 3000 AU. It's not entirely clear why that's the case, but just we do notice that difference, that the temperature seems to fall faster out past a certain distance away from the centers of the hot cores. Zooming out in terms of like comparing the Deep South hot cores to sort of the rest of the galaxy, not in the disk, we find that the Deep South hot cores are usually warmer and more massive than their disk counterparts, at least in the comparison set that we have here. So in this plot, I have the temperature of the hot cores as a function of their mass. The green data points are from the core catalog, which is a selection of hot cores that were studied within, I think, around 5 kiloparsecs of the sun, so they're in the solar neighborhood. The blue data point is from a hot core that was discovered in the outer galaxy. The orange X's are from the W51 region, which is another extreme massive star forming region, and then red is the Deep South, of course. And yeah, you can see pretty distinctly, they skew towards the higher end of the temperatures, and they are much more massive than the ones that are found out in the disk, with the exception of in W51, which also has similarly extreme masses and temperatures. But in spite of those differences, there are some similarities. They have similar radii, namely, when compared to the galactic disk, the skew may be a little bit higher in terms of radius, but overall the radii overlap with all of the other sources. And also, if you generate a radial density profile, so in the core catalog, they also generate radial density profiles. and fit parallels to those and look at the parallel index that they get from that fit. If we do that in Sgr B2 deep south as well, we get our parallel indices. We compare that to the core catalog. We see that the values are pretty similar, but there is a slight offset at around the 2 sigma level. The Sgr B2 hot cores have slightly shallower radial density profiles on average, and so that translates sort of to this idea that as a function of radius, they are denser on average compared to the ones in the core catalog, which may be related to just the mass discrepancy that we saw earlier. I guess I can pause here for a second and ask if there are any questions before kind of continuing on with the results section.
Yeah, I do have a question. I'm sorry if it's a silly one. This is not my domain, okay?
Sure.
I wanted to know the method that you use using the methanol to be the thermometer for those hot cores. Is this the same method that was used to determine the temperature of the objects from the core catalog? Are there? Okay.
So, sorry, I was shaking my head just processing that. They use the same method, but not the same molecule. So that's one difference is I think in the core catalog, they use formaldehyde and methyl cyanide, I believe,
Okay.
which are also, they are kind of commonly used for these kinds of measurements as well.
Okay.
There are some issues in terms of exactly where you're tracing in the protostar, depending on which species you choose, but within several factors, we believe we're tracing, the same structures in the protostars, and we got around that problem a little bit by making sure that the resolutions of our samples were matched reasonably well. So just anything that would be kind of like larger spatial scale would is filtered out.
Yancy.
Yes.
Yeah, when you did the methanol fitting, the plot you showed looked like a pretty good fit to a single temperature. How often did that happen? And did you have any evidence of multiple, like maybe even on the right-hand side, you could see it might flatten out a little bit and therefore there's a second higher temperature component. How often did that really good fits like this happen? Or did you have any evidence for, strong temperature gradients along your line of sights?
That's a good question. In general, I found that the rotational diagrams were pretty well behaved, all things considered. But what I tended to see, so you can see this at in a smaller scale here. I'm not sure if my cursor is visible. Is it visible?
Yes.
Okay, so like what I saw more often than, for example, like a curvature upward or like a curvature downward at low energy was just scatter, like just pure scatter, where you'd have like the lowest energy transition would be low. This transition was always high for some reason, and then it would they just bounce around. But the distribution would still be reasonably well fit by a line. It's just the scatter gets worse. I'm not entirely sure why that's the case, especially namely with the second transition. We spent a fair amount of time puzzling over exactly what that transition was doing, but frankly, we didn't have enough time to really dig into it as much as maybe we would like to. And so just part of the way we accommodate for that is by doing this bootstrapping method to, hypothetically, if we were to have removed those data points, what temperatures would we get, and we factor that into our error.
Yeah,
Dominica?
I have a technical question, so when, I don't know if we should go on with the talk and I can ask them at the end.
Yeah,
Yeah,
maybe that's, but yeah, we'll go on with the talk and then
We'll continue.
you can ask your technical questions at the end.
Perfect. Yes, and thank you for all those questions. That was great. We also measure the methanol abundances in the hot cores, and so just the way we do that is we use the methanol temperatures to compute, along with the dust, to compute the H2 column densities. We make the assumption that the dust temperature is equal to the gas temperature, which is a valid assumption in the density regime that we're working in. The temperatures, the dust and gas temperatures converge in an environment like the CMZ around 10 to the 7 inverse cubic centimeters or so, and we're working in density regimes of 10 to the 9, 10 to the 8, 10 to the 12, 10, and stuff like that. So it works. So we use that to get the H2 column density, and then just take the ratio. And so I have some methanol abundance maps here on the right from where's DS2 and DS1, which isn't terribly important. In general, we find is kind of looking at the population-wide properties. We find that the methanol abundances show a rising correlation with temperature, modulo some variations depending on the source. Every source was kind of its own beast in its own right. In some cases, we weren't able to really dig into the meat and potatoes of like how that impacts the abundances in each source, but just we do see this broad trend still of abundance goes up as you increase the temperature, and then it kind of looks like it's like flattening off or flattening out as you're getting up to higher temperatures. And that's actually consistent with measurements that were taken in 2017 by Ginsberg et al. In W51, where they actually see, this nice rise from low temperatures up until reaching around 250 Kelvin, and then it kind of flattens and starts to drop down. We do, I'll note that we do have temperature measurements that go up all the way up to 600 Kelvin or so, but we don't have abundance measurements in those areas because, those regions are overlapping with an H2 region in Sgr B2S, and we wanted to avoid having to worry about free contamination to the continuum, so we avoided those regions entirely. So correspondingly, we don't have an abundance measurement up there from the because of the lack of H2 column. Zooming out again to sort of like the galactic context, we decided to compare the peak abundance of methanol in selection of hot cores that have measurement like this at comparable spatial resolution. And what we find is that the methanol abundance is generally consistent with modeling that was recently released by Garrett et al. In 2022, that shows that just peak abundance as a function of temperature, assuming temperature is a proxy for time, it is higher at low temperatures, then it kind of drops off as you increase in temperature. One thing that is different between those predictions and what we see is that there's actually this flattening out of peak abundance at higher temperatures, sort of, and also that there's also some outliers to this. So W51E2, I think, has this very high temperature but very high abundance measurement for some reason. And we're not entirely sure why that is. Namely, also Sgr B2N is famous for being just one of the most molecularly enriched objects in the galaxy. It has absurdly high methanol abundances at low temperatures. It's not necessarily news, but this plot, I think, makes it abundantly clear that temperature is not the only property that impacts the methanol or the peak of methanol abundance that you measure. And so there may yet be some formation pathways for making methanol, namely at high temperature in W51, that are still not very well reproduced by the models that we have. And correspondingly as well, there could be the influence of like the lower initial dust temperature in work that has been, in some modeling work that was done previously, found that they were able to reproduce the calm abundances that they see in SAGS B2N, assuming a low dust temperature of order 20 Kelvin or less. So that may all be encoded in this plot. Although we were happy to see that the abundances that we measure they're consistent with a subset of the hot cores that we looked at in the different regions that we were interested in. Last thing I wanted to mention in terms of results was just kind of a brief overture to where SAGS B2S and its neighbors lie in terms of the discussion of young massive clusters. So just for everybody's reference, young massive clusters, are very young, filled with massive star clusters, or filled with massive star clusters that have radii of order 1 parsec and masses of around 10 to the 4 solar masses of stars. What's particularly interesting about these sources in our galaxy is that they show evidence of having a top-heavy or bottom-light IMF, which has been a point of heavy discussion in terms of the validity of that result and kind of how its implications on the universality of the initial mass function. In SAGS B2 Deep South, if you look at the northernmost regions, SAGS B2S and DS's 1 through 5 are all hanging out in this kind of compact central area inside 1 parsec or so. And just looking at the hot core masses, there's around 10 to the 4 solar masses of gas that you see in these hot cores. Now, we can't directly compare from the hot core mass to the mass of stars that will eventually be formed, but just I want to call attention to this region just because that's just the mass that we measure in the hot cores. There's still many low mass dimmer objects that we did not study in the work that I've done so far, and you can see several of them here that are also kind of in this radius. And notably as well, the other regions of SAGS B2N, and AM, have gotten a lot of attention over the years, and rightfully so. They are very extreme, very interesting objects, but SAGS B2S and Deep South have been kind of neglected because they are a little bit more modest. But I think essentially one of the kind of takeaways from the work that I've done is that this region could be an example of an earlier phase of, the young massive cluster formation that people are using the other regions to trace out. And so it would be interesting to leverage these objects and their neighbors just to be able to say, perhaps what's a tentative evolutionary sequence if we assume that these regions are indeed younger than the other 2 regions in SAGS B2. So I guess pivoting away a little bit briefly just for some future work that I'm doing. Currently, as Allison mentioned, I'm at NRAO Charlottesville, working with Chef Mangum on doing a comparison between SAGS B2 and the CMZ of NGC 253, which is a very vigorously star-forming galaxy that has an extremely chemically enriched central molecular zone. Previous work has shown that the CMZ of NGC 253 has significant contributions from the hot cores that are present in this source, just by inference of comparing the abundances of comms in NGC 253 CMZ on cloud scales to the abundances of comms that are seen in Sgr B2 on the cloud scales. So I'm approaching this question we can ask, just like, what is the extent of the contribution of the hot cores to the chemistry and the physics of the CMZ at NGC 253 by asking, or by using some of the molecules that I've identified in Sgr B2 deep south, and then zooming way out and seeing if we can draw kind of like a tentative comparison between the two regions. So ethanol has shown itself recently, at least in the preliminary work that I've been doing, to be a molecule that seems to uniquely trace the compact regions of hot cores in Sgr B2. Like, it doesn't have much of an extended emission component to it relative to things like methanol or dimethyl ether and all of those. And so what I want to do on one hand is use the ethanol to methanol abundance ratio to or to see if you can use that abundance ratio to make any inferences about the physical conditions of the hot cores on the resolved case, and then using that information, do the study again in NGC 253 on the clump or cloud scales and see how they compare. Modulo the limitations, of course, of the differences in resolution and spatial scales that we're probing, but just what happens if you look at the abundance ratios of hot cores in our galaxy and look out at other galaxies that ostensibly have a bunch of hot cores in their own CMZs, and what do you see? And using that comparison, place some constraints on, namely, the protostellar feedback contribution to the emission out in NGC 253. Also, kind of in parallel with that, in the background, I've also been cataloging the composition of my hot cores, since you can't understand these objects with just one species. That just doesn't tell you all of the information that you need, that you can potentially glean from them. And so I've first been cataloging all of the species that are present in the hot cores. And so here I have a slightly out of date spreadsheet that you can see examples of all the species that I've confirmed in green, were suspicious about in yellow, was pretty confident about in blue, and such. And using that information, sort of measure, if it's possible, measure the rotational temperatures, measure the column densities, and start doing abundance ratios between the other comms and H2 or methanol. Not exactly sure, or potentially both, honestly, because that tells you different information. And use that to holistically characterize the physical properties of the hot cores in Sgr B2, just in case, well, yeah, the methanol just doesn't tell the whole story. So maybe, for example, with the ethanol, we're probing deeper into the hot cores, and so we would see the temperatures be warmer or something like that. I had other pictures I forgot about. So just this is an example from the Shimonishi et al. 2021 paper showing that depending on which species you look at, you get different rotational temperatures. And so it's thought that you can use that to probe kind of into different spatial regimes of the envelope. But I know that's become a little bit controversial as well, since there are examples of some complex molecules just floating around out in the ISM. And we don't have very good formation models of how you form them out in the ISM like that either. I'd also like to actually catalog all of the continuum sources that we see in our 1 millimeter data, generate a core mass function just to try and maybe make some inroads into the discussion about, well, Sag B2 and its constituent regions are precursors to young massive cluster. Do we see evidence of the mass function of this region being different than the mass function that you see out elsewhere in the galaxy? And with the caveat, of course, there are some limitations to comparing the core mass function to the initial mass function, some serious limitations to drawing that comparison. But many authors are essentially studying the use of this mass function in terms of being able to predict maybe what the resultant populations of stars will be. And so, yeah, we'd like to do that study here and compare the CMF that we measure at Deep South to the canonical IMFs and also to the artisan quintuplet to see, is the CMF bottom heavy, or sorry, is it top heavy or bottom light? And the last thing, which is something that's relatively recent and I haven't explored too deeply, is just this mass discrepancy between the disk hot cores and the extreme region hot cores. So just, this is the same plot I showed earlier, which is the mass versus temperature. And you can see just there's a clean separation between the core catalog and the outer galaxy hot core, and then there's Sag B2 and W51. We don't have very good explanation for why this is the case, and so I'd be interested to know, is this a real thing? Like, in extreme star forming environments, do you see much more massive and much warmer hot cores, or is there more of a continuum of hot cores, and so we're just missing the sources that we need that are in that gap? I'm not sure what the answer to that question is. I'd be curious to know, namely just, you know, with respect to the questions about the CMZ, does the CMZ's environment kind of predispose protostellar cores to be more massive, or by extension in W51 as well, do the physical conditions that were present in the past in W51 did those predispose them to have higher masses as well? I'm not sure. I would be curious to know. If you see any hot cores anyway, please send me an email about them, because I'm going to try to fill in this plot as best I can. So yeah, that's everything that I really had to talk about today. So I guess I'll leave my summary slide here. Thank you for your attention, and I'll take any more questions you have.
Did you have some questions?
Yeah.
Could you move closer to the microphones? Or shout?
I think you should be able to hear them. Yeah, that's pretty good.
Oh, really?
Yeah.
Hi, very nice talk. Thank you. Can you hear me well now?
Yes.
Okay, so I have a very technical question, so I'm sorry for that. When you showed us the rotational diagram, you mentioned that you are using bootstrap methods to get it. Could you maybe elaborate more about how you actually build the rotational diagrams? Maybe how did you define the area where you were extracting the lines, and whether this is for one of the cores, or yeah, if you could tell us more about it.
So these were taken on a pixel by pixel basis after generating the upper state column density maps for each of the transitions that we were looking at.
Okay, so sorry, let me interrupt right now so I make sure that I understand. So you first made maps, and then based on the column density maps, you built the rotational diagram.
Yes.
All right, yeah, go on.
Yeah, so as far as the bootstraps themselves, well, So the reason that we employ this method is there is like a statistical measure that gives you the error on any a linear fit that you measure, right? But when we made that measurement, it just we didn't take it. We didn't believe it. Honestly, it was so small compared to what the
Yeah,
scatter that
right.
we observe would imply. And so we're like, what's a better way to accommodate for that? And so we implemented the bootstrapping instead to better sample the actual range of values that you get from the rotational diagram. As far as this in particular, this is one rotational diagram from one hot core. There are thousands of these because they all, there's a rotational diagram corresponding to each pixel for each hot core. And so this is just an example of what one looks like. Some are prettier than this, others are very much not as pretty. And just, yeah, you get a range of behaviors depending on where you look. But on the whole, the rotational diagrams are well behaved across the sample, even over the centers. Just the error bars get bigger once you get over the centers, but they're still relatively reasonably behaved.
All right. And if I may ask, why did you decide to first build the condensity maps for each transition instead of taking, I don't know, defining the area and summarizing the flux for each transition and then transforming it into the condensity? So yeah, I don't know.
Yeah,
like,
please continue.
I would rather put some quality cuts on the flux measurement first and maybe just summarize the flux from the whole source and then build the kind of integrated column density rotational diagram on top of that instead of making maps and then extracting diagram out of them. I mean, in principle, you can, I think this is what you've shown in another plot that you can build a rotational diagram in each pixel. However, singular pixel can have unreliable flux, like the one pixel can be very noisy. So if you take into consideration the larger area, that might be a safer approach. So I'm just curious why you decided to go in that way than doing something else. What was the motivation?
So we were interested in doing a resolved study of the sources. That's one thing. Yeah, we didn't want to. Yeah, we wanted to take advantage of the resolution that was afforded to us by the measurements that we have, rather than kind of averaging over the entire source, just in case there was some substructure that was present that we would have missed if we had averaged over the source.
Okay.
Yeah.
Okay, makes sense.
And Desmond, your error bars on the column densities, I assume are dominated by your flux uncertainties for each individual pixel?
Yes.
All right, and you showed two radial profiles, one for temperature and another one for column density. And the one for column density was much less noisy at the end, while the one that you just showed before, is so the temperature profile is very noisy at the end. What happened between, like, I would expect that the column density profile will be also noisier when you go outwards.
So yeah,
Maybe I see something.
I believe that that's coming from, so this is, sorry, just to be clear, like you're saying like the error bars are not
Yes.
larger here, but okay. So I believe that that's coming from this is the radially averaged density as you move your way, like move out of the core. And so the air, sort of like you're mentioning with the flux a little bit, over 1 pixel, the error, like just looking at a small area over the centers of the cores, the error is relatively large. But as you average over out, out to large radii, the relative the relative size of the error compared to the measurement that you're making is going down because we're including so many, you know, there's I'm not sure how many pixels are included in some of the inner ones, but out to the radius of the core, it could be,
Yeah, but
hundreds
then,
of pixels.
but for temperature, you still have very large error bars outwards. Yes. that's
Oh,
one.
sorry. No. I'm sorry. This is not error. That is actually just the range of
Oh,
temperature that are
okay.
measured out at
All
you know,
right.
peak temperature, and some of the like the high temperature values, some of those are probably extremely, like they're very close to, they're like right at 3 sigma or so.
Oh.
But yeah, it's not error. Sorry about that.
Okay, no, I'm
Okay,
sorry, thank you.
clarified. Right. Good question.
Yancy.
Yeah, while the temperature profile, that's what my question's actually about. I've been really curious about the fit to this. It's really, really shallow in terms of the radial temperature distribution. Of course, that's a average line of sight rotational temperature measured all the way along and then made into a radial profile. But I'm really curious why it's so flat. I would think you have these really bright internal sources in the middle, and they're really heating things up. But then maybe it gets so optically thick that is most of this heating really coming from maybe like the interstellar radiation field that's surrounding the core? I'm curious why you might think there, or if you have any ideas why this isn't a steeper profile in terms of the temperature.
That is a fantastic question. So we've talked about this a little bit, but I'm honestly not even sure, because at first, my first like gut instinct is, so admittedly, this is just my gut instinct rather than something more empirical. My gut instinct would be that the interstellar radiation field is not contributing that much to the heating.
What is
But
the radiation field here?
for this source, it's probably around 3,500 AU or so.
Yeah, and do you know, like, have an estimate of like what kind of G naught might be, like in terms of the interstellar radiation field strength? Like, is
It
it
is higher.
higher in this region than it is like in the local ISM?
Yeah, I am admittedly blanking on the exact value for that, but I do know like it's significantly higher than the solar neighborhood. Thinking about it, okay, yeah, it's certainly possible that like probably the local cosmic ray field is probably the the more important heating source rather than other things, just because the cosmic ray ionization rate in the CMZ is, I think it's like 2 to 3 orders of magnitude higher than in the solar neighborhood. So it's certainly, as I'm like thinking about this now, yeah, it's certainly possible that like this could be an artifact from the
It'd be really
ambient
interesting,
cosmic
because
rays.
this is, I think, an interesting result for somebody that does a lot of core modeling, like on little guys that are nearby and low mass. The inner storage field is important, but I think you could probably do something like run a RAD-MC 3D, like, a dust continuum rate of transfer model, pop in your density profiles. You're going to have to put in a lot of photons in those MCMC models because you got such enormous densities. Matter of fact, I don't even know if it'll be able to handle 10 to the 10 towards the inside. That's crazy impressive density there. But I'd be really curious about this, like why it's so shallow. Is that an artifact of doing line of sight averaging of rotation temperatures? Or is a real temperature profile really flat in these cores? And why aren't they fragmenting? I can think of all kinds of cool questions about the density and temperature profiles that you have here. So thank you for a very, very nice talk. I really appreciate it.
I would point out that like we do expect that the cores do like what we see at 3000 AU is not the end of the story. Like there's definitely substructure inside these things. In some cases, at least. In this particular source, maybe not. But at least for some of the others, there's definitely it's extremely unlikely that it's one singular object that's responsible for this. I know that some cosmic ray ionization rate studies have been done in Sgr B2N. And so I think related to some of these questions, I'd be interested to see, like, I don't know if anybody's done this before or exactly how it's done, but like if there'd be a way to make like an actual map of the cosmic ray ionization rate across Sgr B2 and use that in terms of, you know, like plugging that into a model to try to reproduce this behavior. Just because I know that these regions are so special that I think even, well, perhaps I shouldn't say, but I know there are maybe some questions in terms of like the uniformity of the cosmic ray ionization field across Sgr B2, like because Sgr B2N in particular is such a insanely dense source. Of course, all the high energy cosmic rays are still going to be able to get through, but just like actually seeing, you know, are the massive stars, are the cores in Sgr B2N seeing the same flux that things in Deep South are, where things are less dense? I'm not sure. I'd be curious to know.
I have a question about the G naught. So,
Yeah, so it's 12:59, so one last question.
yeah, so Jens just asked, it's hard to actually get from UV for that data because it's very extinctive. But is there an estimate about the order of 1,000 of G naught or something higher?
I think so. Yeah, I do think it's of order 1,000. I don't remember how that measurement was taken.
Okay, it would be really interesting to see what G naught that might be in this region.
Yeah, it's definitely like the entire CMZ is just of order, like the canonical value we keep in our heads is 1,000 G naught or so.
Thank you.
All right. If anybody has any additional questions, please feel free to contact Desmond or contact me and I will forward to Desmond. Thank you all so much for coming. Thank you, Desmond, for giving a very nice talk today. And we will see you all next week.